pleasure to introduce Professor Yu He. Today as our speaker, Yu mainly uses light matter interactions to investigate correlated electronic systems and other functional quantum materials with an emphasis on high TC superconductivity. Yu started his assistant professor position at Yale University in the Department of Applied Physics this fall. He obtained his Bachelor of Science degree in physics from the University of Science and Technology of China, otherwise known as USTC, working with Xianhui Chen on synthesis and characterization of novel iron nictide superconductors, even in the early days of his undergraduate years. Then he went on to obtain his PhD in applied physics from Stanford with a master's in electrical engineering, working in the group of Ziek Shen, and did some really outstanding work on the high TC cuprate problem, resulting in a number of very high profile papers regarding the understanding of the role of electron-phonon coupling, weak coupling superconductivity, and superconducting fluctuations on the extreme overdoped side of the phase diagram. He then, at the end of his PhD, already signed on his current position as an assistant professor at applied physics at Yale, but chose to go on to work as a prestigious Miller Fellow for a year at the University of California at Berkeley, where he complemented his prior expertise on material synthesis and ARPAs by experiments with inelastic X-ray scattering and also neutron scattering on cuprates and other quantum materials before officially starting his position this fall. And so today he will tell us about his recent very exciting results on fluctuating superconductivity in a metallic high TC cuprate. So without further ado, you can take the floor, and I will keep an eye on the, I think you can just ask questions in the middle, and I'll keep an eye on the chat window just in case.
Sure, sounds good. Thanks, Ming, and good afternoon, everybody. It was such a treat to step into the internet and be here virtually. Yeah, I recently went to an online K-12 outreach event that I was just telling me about. I was tasked to introduce high TC superconductivity to high schoolers and middle schoolers. And in the end, I find this give the most successful take-home message. Since Halloween's still fresh, I hope you're already convinced that high TC is still a useful subject. So among all the 30 years of roller coaster rides and evolution of high TC topics, I'm going to tell you something today about superconducting fluctuations that we think may really have brought us one step closer to the finish line regarding the high TC problem. So in today's talk, I'm going to spend about 60 to 70% of time on raising high TC superconductivity awareness and the rest of the talk to show some recent data. Okay, let's get started. So first off, this work is a part of a long string of efforts to tackle the high TC problem. It's one of the most recent development of a growing collaboration that have addressed my professional career so far. In particular, I think these collaborations underscores the importance to rally from all aspects in order to reduce variables in a highly complex problem like the cuprate problem. So I think it all started with a promise. Shown here is a special evening session of the 1987 APS March meeting, which was later known as the Woodstock of Physics. I'm always jealous of those who get to attend this highlight moment in person. So people stayed till the wee hours of the morning to share the excitement of this discovery of this magic perovskite oxide that shatters all superconducting record overnight. So it was such an eclectic time that for the very few times in history, physics made it past the politics to the cover of Times magazine. So there was a promise. Everybody thought that with this new breakthrough in superconducting technology, room temperature superconducting applications going to come close. So this plot of high TC versus year of discovery must be very common sight to you. I draw this cartoon on the right. So in 1993, it's no brainer that one would study high TC because TC is high. But more than 20 years later, the promise seemed to be still on its way. And it could be in an awkward silence sometimes to address the same question. I get asked all the time, why still cuprates? Not only in front of young students, but also more painstakingly in front of program managers and funding agencies sometimes. So I would make it a case. Here's the manifesto. First off, I think cuprate has such a long research lifetime, not because it's hard. On the contrary, it's partly because it offers one of the simplest type binding electronic structure among all the gazillions of quantum materials out there. So what is shown here is the simple plot of the first Brillouin zone, as well as the type binding band structure of a typical cuprate. So with such mathematically traceable starting point, now we can sprinkle the system with some real hard problem, namely the electronic correlation. So in this case, cuprate often serve as a model system to study new concepts and emergent phenomenon, charge density wave, pseudo gap, Mottness, even recently Planckian dissipation, you name it. So in comparison, I always joke with Ming that if one were to be daring enough to perform detailed cuprate type RPS analysis in multiband systems such as quantum spin Hall candidates, tungsten ditelluride, or iron pnictides, the referees are going to be like this and they're going to unleash hell. So that's one aspect of why cuprate is important and has survived such a long time of investigation scientifically. But in the meantime, cuprate high TC systems are of such forgiving large superconducting energy scale that it also propelled and motivated a lot of critical advances in instrumentation and methodology developments, ranging from sub 100 millieV resolution self-factory rigs to discover the charge density wave, or multiplexing detector in high resolution RPS, or to quasi-particle interference in scanning tunneling spectroscopy. So cuprate is like this one big nail that is big enough to test almost every hammer. So that being said, I guess in the spirit of scrutinizing a simple textbook subject by pushing to the extreme of instrumentation, I'd like to bake this following two questions in today's talk. One is, how conventional, after all, is overdoped cuprates? Overdope here means we push a lot of holes or carriers in general into those oxide perovskites. And the second question is, moreover, can we finally say anything about the mechanism of high TC superconductivity in this supposedly simpler phase region, which I will give you a little bit of introduction about. So to tackle this problem in a methodological way, this is to-do list, which will serve as outline to today's talk. First, we want to find a theoretically and experimentally tackable system, meaning that it needs to be feasible. The second is we want to then reduce the role or occurrence of correlation physics. We want to reduce the electronic correlation as much as possible. And then we will check the textbook BCS properties item by item. And towards the end, we're gonna gather those that still don't check out with textbook BCS properties, even in these supposedly very metallic regime. And we want to find out why. And of course, very end, hopefully we're gonna write a paper. Okay, so suppose tomorrow is your solid state physics final, and you just learned that something called high TC cuprate is going to show up on the test sheet. What are you going to do? Well, besides praying to the high TC god, the next 4 slides are going to be what I would put on my cheat sheet. So let's first start from a lattice structure whenever we talk about new material. So cuprates are those type of material that are innately layered. What is shown here is a mercury-based type of cuprate, where you see TC increases from left to the right, to the middle, and then reduces to the right. And the key structure motif among all these cuprate perovskites are these CuO2, copper O2 layers. And you can see from left to the right, the copper O2 layer increased from 1 to 2 to 3, all the way to 5 layers per half unicell. And this copper O2 layer is singled out on the bottom. And you see that every copper are connected to the other copper by intermediate oxygen. So The next thing we want to learn about is the electronic structure of cuprates. So in these materials, the copper is caged in either octahedral or pyramid. Therefore, its 5d orbitals are going to be split first into 2 EG orbitals and 3 T2G orbitals. And then because the octahedral is not perfect, so it incurs a further energy level splitting into a tetragonal geometry where the dx squared minus y squared orbital is elevated to the highest energy. Of course, the copper atom hybridizes with the oxygen 2p orbitals. So at the end of the day, we're going to live with a hybridized orbital content of oxygen 2p and copper 3d orbitals close to the Fermi energy. So we know in cuprates, copper takes 2+ valence state, more or less. So the valence electron configuration will be 3d9. And if we were to fill up all the 5d orbitals, we're going to see that it is the topmost dx squared minus y squared orbital that's halfly filled. And if we were to expand all these orbitals into bands, in a tight binding type of thinking, where the high symmetry points here, M, gamma, X, are denoted in this square tetragonal Brillouin zone, we see that the dx squared minus y squared orbital, or band in this case, is the one with the highest kinetic energy. And it's almost the only component for those electrons living near the Fermi level. However, we also know due to the spatial constriction of the 3D orbitals, the electrons are really close to each other. Therefore, they have very strong Coulomb interaction with each other. That prohibits a double occupancy on this dx squared minus y squared orbital because you're going to be penalized by a very hefty Coulomb energy gain. Therefore, in half-filled cuprates or stoichiometrical cuprate, you get insulating state near EF. So material is half-filled, but it's insulating. Transport-wise, we can actually replace the positive ions with different positive ions in those cuprates, therefore introduce effective carrier doping. And we see that in this particular case, lanthanum 214 system, by replacing some lanthanum with strontium, we can introduce whole carriers into the system. And you see, as the strontium replacement goes up, the resistivity actually start to change its behavior from an insulating system to more and more progressively a conductor, a metal. And this metal to insulator transition, sorry, the insulator to metal transition as we introduce more holes into the system is accompanied by a continued reduction of C-axis over AB plane resistive anisotropy in cuprate. So you can see that the system also becomes more and more three-dimensional when you introduce more holes in there. So with all that in mind, you might have seen many versions of cuprate phase diagrams in the past. It's really a basket of apples and oranges because they draw observations as a result of different probes. So a word of caution, take those different phase diagrams with a grain of salt. But the general features are those such that starting from half filling, when you introduce more and more hole doping into the system, there is a long-range antiferromagnetic order that's going to be quickly killed, and about 5% of hole doping superconductivity sets in. In these underdoped all the way to around optimal doping, there's all kinds of emergent electronic phases showing up. But once we go past optimal doping, or to be more exact, past certain critical doping shown here, the system suddenly loses most of the signatures for those emergent orders, and they start to behave suddenly much less strange. So the low energy electronic structure evolution also follows the spirit of the phase diagram that we just drew in the previous slide. Now I keep it on the upper right corner. We're only going to talk about the hole doped side for today's talk. So we see that for these electronic structures, at half filling, there is a large energy gap near EF, and everything is incoherent. The electronic correlation is very strong. So as long as we dope the system by a little bit of holes, a very coherent part of Fermi surface, or a lot of quasi-particles, as we call it, start to emerge near those gamma x direction, or 0 to pi direction, which we sometimes call nodal direction. However, those quasi-particles aren't really showing up near the endpoint, or the 0 to pi 0 direction, where the spectrum remains very, very broad. And only after we dope the system past that critical doping, the band structures start to behave like the tight binding prediction, and the Fermi surface becomes restored to this coherent Fermi surface over the entire momentum space. Last but not least, neutron scattering measurement have measured the magnetic scattering strength in these systems. And we see that the magnetic excitation, in this case, momentum integrated S of omega, reduces quickly as more and more holes are introduced into the system, which speaks to rapidly vanishing magnetic fluctuation strength as we overdope the system. And back then, it provided a basis for people to think that magnetic fluctuation can be potentially the parent glue, because it disappears together with the disappearance of the superconducting dope. All right, these are the crash course on cuprates. But the last but not least, a very important aspect is regarding the superconductivity itself. So in cuprate, we know it's a D-wave superconductor. You must have heard about it. D-wave in the sense that if we were to plot the superconducting pairing energy as a function of momentum, it shows A, a large anisotropy, and B, the order parameter actually changes sign when we go from one quadrant to another. And this sign changing property actually enforces a zero gap direction, or two zero gap directions in the system. If we were to overlay the Fermi surface that we just draw on the previous slide on this one, we can now see that why we are calling gamma x direction the nodal direction, because the gap has a node along this direction. And the gamma m direction is called antinodal direction because the superconducting gap is maximum along this direction. So we know that as we introduce more and more holes into the system, if one were to measure the superconducting D-wave gap size, it actually remains more or less a constant over a large part of the doping axis, but only start to precipitously drop as we sufficiently hole dope the system. So all of these comprises the basis for the understanding of the cuprate physics so far. Now let's get back to our outline. And with the two questions in mind, let's start with the first item on the to-do list. Let's try to find a theoretically and experimentally tackable system. Since our goal is to perform an all-out attack, a coordinated attack on this supposedly simpler regime where we introduce a lot of hole carriers into the system, we really want to find a system where all kinds of techniques can apply. So listed here are some of the most frequently used spectroscopic and transport experiment techniques. And listing together with these techniques are those cuprate systems that are commonly deemed feasible for that particular technique, either due to the detailed requirement of the technique or the microscopic processes involved in those probes. For example, with neutron scattering, we get to have a detailed measure of the structure factor, dynamic structure factor. So we get to have a hint on how the bosonic excitation looks like in the system. And say with photoemission or with scanning tunneling spectroscopy, we get a direct hold of the single particle spectral function, which we get to directly observe the charge degree of freedom, the single particle excitation in the system. And of course, we have our thermodynamic police. However fancy our microscopic model can be, it must satisfy those free energy evolutions, since superconductivity at the end of the day is still a second order phase transition as we know it. There's also material specifics where certain cuprates can only be doped within a certain Hove concentration. And in order to achieve this Hove overdoping, to press sufficient Hove into the system, only a handful of systems are feasible. And we also want a system with large enough energy scale. So all of these possible techniques can provide comparable data quality and resolution. So with all of these constraints in place, we see that a bilayer cuprate, bismuth 2 strontium 2 calcium copper 2 oxygen 8, or we do a shorthand bismuth 2212, becomes the most promising candidate that can sort of assemble all the information from different techniques. And importantly, for this current study, we want to steer clear of these correlation physics. Therefore, we want a sufficiently high Hove doping. And on the other hand, we also want the system TC to remain high enough to be interesting and to be friendly to our experimental techniques. So we have a threshold on TC. And therefore, on this superconducting dome temperature doping phase diagram, we carve out this little sliver of golden region where a Hove concentration is between 20% and 24% per copper that we're going to focus our following study on. All right, so let's go to the second.
Can I interrupt you for just a second?
Yes, please.
So just sort of orient myself. I think for thorium 2201, there's some old result on maybe some resistivity and isotropy type of measurements for the information about the Fermi surface in the overdoped regime. I just wonder how much was known in other of the overdoped systems on this large Fermi surface. That's a background.
That's a very good question, Timia. So for thallium 2201, that initial quantum oscillation work mapped out a large Fermi surface. I think the observation was pretty clear where the oscillation frequency is high. But the argument can always be that so long as you have high enough field and a low enough temperature, you always can get quantum oscillation. So for other cuprate systems, in particular, bismuth 2201, the single layer cuprate compound, and bismuth 2212, the bilayer cuprate compound, large coherent Fermi surface has been observed all the way up to the point where superconductivity disappeared. And the volume actually is comparable to those measured in the thallium system. I hope that answers your question.
Yeah, so the 1 minus X has checked out pretty well.
No, you mean 1 plus X?
Oh, 1 plus X, yeah.
Yeah, so there is qualitatively, there's a rapid increase of Fermi surface volume across some doping range in the overdoped side. But quantitatively, it doesn't really always agree with X and 1 plus X. So Endo and Greg Bobinger has a follow-up work with a high magnetic field measurement of Hall coefficient. And it's sort of in direct contrast to Louis Taifa's report. Yeah, those are, I think, more technical details. And
yeah, we can come back to that.
We can chat afterwards.
I mean, right, no, but I mean, it would be good to have some APAS information on such things.
Yeah, so
Yes.
let me ask you, yeah. So in the overdope regime, I mean, is this supposed to be homogeneous or inhomogeneous? I thought there was some earlier claim saying the overdope regime is actually have a puddles, right?
Yeah, Pengcheng, I think you also asked, or you already asked one of the content in the later slides.
Okay,
So,
go ahead.
But to put it short, when we talk about homogeneity, it always has a length scale attached to it.
Sure.
So STM has already observed those nanometer scale inhomogeneous electronic density of state locally in overdoped system. And in particular, this is not just specific to overdoped cuprates. It's persistent for all dopings. Then we start to talk about chemical inhomogeneity. These inhomogeneity may be characterized by either thermodynamic or magnetic measurements. And those type of inhomogeneity are small. So I think in that case, we have to treat it in 2 different ways. If we talk about nanoscale electronic structure in homogeneity, it's always there. But if we talk about, say, if the bulk TC transition is sharp or not, then it can always be made very sharp.
Okay.
All right, let's keep going. So now I think we're ready to move on to the second step. Let's take it slow and pedagogically. We want to reduce the correlation physics as much as possible, so to make our life easier. So the way we do it, we go all the way from the crystal synthesis, we mix powders, put it in an oven, get those crystals, pressurize it, and put it in a pressurized oxygen vessel. It's similar to those stuff that you use to make popcorns, the puffing guns. And afterwards, those nice millimeter to sometimes centimeter sized crystals pop out with a high level of enriched oxygen in them. And you can imagine that when there's a lot of oxygens pressed in there, they're going to grab onto electrons. Therefore, effectively, you're going to have more Hove carriers in the system. To see that we're successful, we're effectively making the system sufficiently Hove-doped, we can perform a quick photoemission measurements near the beryllium zone boundary, or near what we call the antinode that we introduced earlier, and look at how the spectra suddenly becomes a lot more coherent. So what is shown on the lower right bottom are two what we call antinodal spectrum, where the vertical axis is binding energy and the horizontal axis is parallel momentum, shown in the red bar here. The left picture shows a system with TC of 92 Kelvin and effective Hove doping of 18%. And above TC, you see there's already some gap showing near Fermi energy, and it's used to be known as the pseudo gap. And now we know it's a mixture of fluctuating superconducting gap and pseudo gap, which will be discussed in more detail later. Importantly, on the right-hand side, only with about 4% more introduction of Hove carrier concentration, system TC is suppressed to 66 Kelvin. But you can see it even without any quantitative analysis that the spectrum becomes qualitatively a lot more coherent and the same momentum point in the beryllium zone. So that's already giving us a lot of spectroscopic confidence that we indeed have pressed enough oxygen into the system such we regained spectral coherence. All right then, the next thing is of course to check transport and magnetic properties. So we can measure the Dirac-Meissner effect, put the crystal into an MPMS. And we see that when the magnetic field is perpendicular to C-axis, there is a rather steep drop of magnetic susceptibility. And when we put the magnetic field parallel in plane, due to the anisotropy of these quasi-2D superconductor, there is much smaller magnetic shielding effect. In the meantime, we can also measure resistivity both in AB plane and along C-axis. And we can see that first, the resistive zero temperature aligns with the diamagnetic signal onset temperature, which is consistent with the superconductor's behavior. And the second thing is that the resistive anisotropy is now reduced only to a few hundred. It's still respectable, but it's reduced by more than 2 to 3 orders of magnitude comparing to optimally doped bisco. So to put it short, we see that the system becomes a whole lot more metallic and a whole lot more isotropic comparing to optimal doping here. All right. So now we know we have pushed enough oxygen into the system. We can now start checking textbook BCS properties item by item. And we want to see whether the superconductivity in this regime can really be captured by a model or framework that we are familiar with. So this is not meant to be a solid state class, so I'm just going to very quickly flip through it. But we really need to ask the question, what are the BCS premises that we're going to investigate? One thing is when we deduce the Cuprate instability, namely when there is an infinitesimally small attraction between electrons on the Fermi surface, there are going to be a energy gap opening to save the energy. And in order to get that Cuprate instability, there is a critical assumption that has to go into the derivation, which is the presence of a well-defined sharp Fermi surface where the pairing action happens exclusively on or in the vicinity of it. Therefore, this requirement of Cuprate instability already requires a quasi-particle theory, meaning that we have to have a sharp Fermi surface and a well-defined energy momentum relation. Note that this is not satisfied in optimally doped cuprate or underdoped cuprate, because we said the spectra are extremely incoherent and we lack a full Fermi surface. On the other hand, BCS theory is also a mean field theory. When we look at a microscopic pairing field, again, I don't plan to go through the details and you should not read through the details. But what's really important to call out is the mean field approximation to single out the pairing field delta. And use that approximation, we can essentially derive the BCS ground state wave function and the ground state eigenvalue. And what this is telling us is that first, due to this mean field approximation, there's almost by definition zero superconducting gap fluctuation in the system. And the second thing is BCS theory assumed a much larger bandwidth than the pairing energy or the superconducting gap size to satisfy the Coulomb retardation approximation. And what that means is that only in a tiny bit of momentum vicinity around the Fermi momentum that you're going to get substantial electron-hole mixture once you go from above TC to below TC. In other words, if we were to really write down the number density fluctuation in a BCS superconductor, it's going to scale with the ratio between the gap squared divided by the dispersion squared plus gap squared and summed over the entire momentum space. And if we were to follow the BCS premise, that's telling us that there's only a tiny bit of momentum region where particle and hole, electron and holes are mixed. Therefore, this ratio after momentum summation will tend to zero because epsilon k will always be much larger than delta k. Therefore, there is a self-consistently negligible fluctuation in the BCS superconductor. So don't worry if you don't get any of the mathematical details, but what I really intend you to take home is that BCS theory is a theory that needs quasi-particles in the normal state, in a metallic normal state. And it has little fluctuation to begin with due to the mean field nature that the framework is set up. A good example is lead. So if we look at lead, the superconducting coherent length is about 83 nanometers. And the carrier density in lead is about 40 per cubic nanometer. Therefore, we see that within one coherent volume, we have about 10 million pairs of Cooper pairs overlapping with each other. And in this notion, the Cooper pair footprints highly overlaps and there can be very little fluctuation. The phases are highly interlocked. This is evidenced by, say, the heat capacity, specific heat signature of the superconducting transition in lead, where you see that while TC is around 7 Kelvin, the transition is so sharply jumping around the transition temperature in such a nice mean field form that the transition width is less than 10 millikelvin, less than 1,000th of the actual transition temperature TC. So this is what a mean field BCS superconductor should look like. All right. So if we were to talk about superconducting order parameter, there is an amplitude part and there is also a phase part. There are a type of BCS superconductors where we know in the high temperature, there's no electron pairing and there's no phase coherence. But once the temperature drops below some pairing temperature, the electron pairing and phase coherence develop at the same time. So those are the BCS superconductors where we've considered pairing limited. But there is also another type of superconductor, excuse me, where at high temperature, there's no pairing, there's no phase coherence. But below certain characteristic temperature, electrons or holes start to form pairs first without establishing global phase coherence. And you can see in this region, because the free energy term has a term that's proportional to the spatial gradient of the phase squared, there will be additional energy penalty to the lack of phase coherence. And only when you further cool down the system will develop a global phase coherence between the electrons. And in this case, zero resistivity state is reached, and we get a bulk superconductor. So the second case, the phase coherence limited case, is a case that is rather non-BCS. And it could be either due to low dimensionality, as indicated by, say, costless-solid transition, that some of you must know, or it could be due to disorder or granularity, or it can be due to low carrier density, or simply due to the pairing being too strong. So in this case, the BCS premise is broken, where the kinetic energy of the electrons becomes much, much smaller than the pairing energy. Therefore, the pairing becomes highly localized, and we traverse into the BEC limit. Actually, in cuprate superconductors, especially those underdoped cuprate superconductors, measurement of superfluid density with muon resonance or with optical reflectivity, or very recently from the very own physics department of Rice with the shot noise, people have observed signatures of strong fluctuating superconductivity and low phase coherence in those underdoped to even optimally doped cuprates. So therefore, back then, in 1995, Victor Emery and Steve Kivelson proposed this very famous phase diagram to explain this domed shape superconductivity phase region in the high TC phase diagram. Whereas when we introduce horizontal axis is Hove doping, when we introduce Hove doping, first, the phase coherence becomes better and better, while the pairing interaction becomes worse and worse. Therefore, in underdoped region, it's a phase coherence limited superconductor, while in the overdoped side, it's a pairing limited or BCS type of superconductor. And with that understanding, we flip these photoemission measured spectra near the antinode, where the superconducting gap is supposed to be the largest in the normal state. And we see that indeed, on the looking at the phase value, above TC near optimal doping, there is some kind of spectral gap here already. While in sufficiently overdoped sample in the normal state, there is no more spectral gap anymore. So now we're ready to check what are those expected behaviors, BCS behaviors in the overdoped cuprate. First of all, we can perform photoemission measurements of the entire Fermi surface. And this is one of the aspects that Chimiao asked a little bit earlier. We see that at 22% Hove doping, there is a coherent continuous Fermi surface extending all the way from beryllium zone boundary to beryllium zone boundary. In comparison, if we just look at 18% doped bisco, and you see that near the antinodal region, it's a blob of intensity, which we now know as a pseudo gap that doesn't have any sharp quasi-particles or clear dispersion. If we look at the temperature dependence of the energy distribution at this particular momentum point at pi0 at antinode, here energy axis is perpendicular going into the screen, and we do it as a function of temperature for this overdoped bisco. We see that from high temperature to low temperature, the spectra continuously sharpen as we lower temperature. So it behaves just like a metal, or like in a Fermi liquid, where the quasi-particle lifetime becomes longer and longer when we lower the temperature until we go below TC or T gap, where superconducting pairs form. In contrast, this is a literature work by Makoto Hashimoto in 2015, that if you were to look at the same spectral evolution, but in near optimally doped sample, you see that going from high temperature, which now is the bottom curve, to low temperature, there's always a finite spectral gap at the Fermi energy, happening way before TC is reached. So this is in stark contrast to the spectral behavior we observe in the sufficiently overdoped cuprate, where everything just looks like how a normal metal you would expect. There's a second aspect where we can just measure the superconducting gap and TC as a function of doping. And we see that with sufficient Hove doping, the superconducting gap to TC ratio drops down from a very large non-BCS value to some value that start to become very close to the BCS, D-wave BCS limit, which is a dashed line here. So at 22%, it's slightly above BCS limit. And last but not least, we can also measure the superconducting gap shape as a function of momentum. So here is a momentum resolved superconducting gap plotted as a function of a D-wave parameter, 1/2 cosine kx minus cosine ky. And we see that at the lowest temperature, it can be described rather well by a D-wave form, which should show up as a straight line in this horizontal axis. So all of these checks out with expected BCS D-wave weakly coupled superconductor behavior. But we notice there's a small band structure nuance, where if we were to look at the local band structure along the Brillouin zone boundary, we see that along the boundary, there is a very shallow Van Hove point, a very shallow local band bottom, or a very shallow band top if we were to look at the perpendicular direction, that are very close to the Fermi energy. And they're very flat. They're flat to an extent that extend all the way almost to 30% of the linear dimension of the Brillouin zone. And we can extract the BCS correlation length based on the Fermi velocity and the gap size we measure experimentally. And we see that it's only about 9 angstrom. So this is only 2 to 3 lattice constant size. This is very short correlation length. Therefore, superconductivity will have an innate tendency to heavily fluctuate. And therefore, after noticing this band structure nuance, we already think, maybe there's some merit for superconducting fluctuation given that very shallow, flat, near antinodal band structure. So to put it pictorially, we have already seen the BCS and BEC limit on 2 ends, where in one case, the kinetic energy is much larger than the pairing energy, and in the other case, the kinetic energy is much smaller than the pairing energy. However, in overdoped BISCO, the kinetic energy itself is still much larger than the pairing energy. However, to the extent of thermal excitation, where the electrons are thermally interacting, there is a substantial region of the momentum space that are rather flat. So we turn to bulk measurement, and we want to see if there's any thermodynamic signature for such strong fluctuation. And first off, we can measure heat capacity. And we see that, so the near straight line is the raw data, and due to the large phonon background, we just subtract out the straight line. And we see that, first off, the superconducting transition indeed shows up as a near singular transition at 66 Kelvin. But there is a much extended temperature region above TC, where heat capacity already start to elevate. And secondly, we can also measure lattice expansivity, which is another thermodynamic quantity that's sensitive to a second order phase transition. And we see similarly that there is a same divergence around 66 Kelvin. But again, the response started at a temperature way above the bulk transition temperature. And this is in stark contrast with the classic textbook BCS superconductor, where the transition is so sharp, so mean field-like, that there's negligible fluctuation temperature range. And what's really important is all of these happened under a rather metallic normal state. That's why it's really non-trivial. We can estimate the carrier density to be almost 10 to the 22nd carriers per cubic centimeter. That's very, very high carrier density. So all of these makes this observation of extended fluctuation region rather non-trivial. Now we can use photoemission to examine the momentum structure of that spectra. So what is shown here is a very high statistics, high resolution scan just along the Brillouin zone boundary. And we can divide out the Fermi function because we have such good statistics to recover some of these upper branch of the Bogoliubov quasi-particle dispersion. The top two panels are below the bulk TC, and the bottom two panels are above bulk TC. And I hope you agree with me that there is still a substantial band structure anomaly or disruption at the Fermi energy, even at 13 Kelvin above TC.
Sorry, could I ask a question of clarification? This is Andrei Nevedomsky.
Sure. Yeah.
You mentioned the flat band near the M point, and so could you point it out in this cuts? Where is the flat band that you're referring to?
Okay. So let me. Yeah. So if this were to be the Brillouin zone,
yep.
The false color plot you just saw in the previous slide is the cut along the zone boundary. So it's the top cut. Mm-hmm. So in this case, you don't quite see the flatness, you just see the shallowness. But this is a shadow point for a tie binding band structure. In other words, if you were to look at the band structure in a perpendicular direction, going from zone center to the zone boundary, it's this band. I zoomed in to only 100 millielectron volt energy window, so it may not look as flat. But you see, up to half of the linear dimension of the Brillouin zone, the band structure remain within 100 millielectron volt. And over the rest half of the Brillouin zone, it drops all the way down to 1 eV. So to put it in that scale, this region is rather flat.
Are you saying there is a kink, like a famous kink feature seen in underdoped cuprates?
In the superconducting state, you will see this region being compressed to even flatter. Yes, and there is a small kink here, around 50 millielectron volt.
Well, I'm just going by what you said, is that over 2/3 of the Brillouin zone, you only have 0.1 eV, which means the slope, this parabolic slope is relatively flattish, right? And then you're saying then it plunges down to -1 eV. Are you saying there is a kink?
Yes, right. The kink is somewhere here, exactly around the boundary of the plot. It's going to suddenly becomes really, really rapidly falling down to 1 eV when you go towards the Brillouin zone center.
I see. And sorry, one last question. I don't mean to dwell, but could you say how generic this is? So I understand your observation is an overdoped. Has something like this ever been shown if you scan from gamma to M point in other cuprates, optimal doped or otherwise?
Yes. The problem for optimally doped cuprate is the antinodal spectrum is very incoherent. You don't really have opportunity to really call out a concept like dispersion. You just see a blob of intensity here. Only when you go into superconducting state, you recover the quasi-particles near the antinode. But you can't do a similar plot of this kind in the normal state as we do here for the overdoped system.
Fantastic, thanks.
Sure.
So this unmeasurable kink that you've seen, I mean, is that due to electron phonon interaction or what?
Not 1 millivolt. It's about
100 millivolt. Yeah, 0.1 eV. Yeah.
Yeah, so I don't think that's a result of electron phonon coupling because the highest energy phonon in cuprate is about 80 millielectron volt.
That's right. Yeah, but
and it's also, sorry, Pengzhi.
Yeah,
go ahead.
It also cannot be due to magnetism, right? I mean, there's no spectral weight, just like as you're saying, right?
Yeah, right. So this is something very peculiar, and we think could be a generic electronic correlation that sets the low energy electronic structure landscape. The reason is we may call it a kink, but if we really look at the dispersion, it's a continuously bend down. It just bends down quicker and quicker until it plummets to the gamma point. So it's not really like a electron phonon coupling kink in our conventional understanding happening in the very sharply centered around the energy. Not really. Everything just evolves continuously, but it just plummets faster.
Okay.
Yeah. Sorry, I think it's dragging a little bit longer than I thought. So
I don't want to slow you down, but super quick. So in say panel H here, what should I stare at? Panel H on the left there. No, you had it.
Oh yes. Yeah.
So where you said okay, I should look at this and see, aha, even at this temperature, I'm still seeing Is it basically the fact that I'm seeing some kind of real difference between panels H and I? That's the thing I'm supposed to notice, that like the shape, I mean, they're, you know, that the shape right around the Fermi level is a bit different between panel H and panel I?
Right. So first off, you're not supposed to call it out just from the false color plot. I'm just trying to tease out, there's some visual anomaly already here.
Yeah.
It doesn't look like a continuous parabolic dispersion or continuous dispersion.
That I buy. Yeah. Okay. Okay. Thanks.
Yeah. Now we can be a little bit more quantitative. That's what we do in photoemission, right? This type of analysis, if I were to do it in a multi-band system, I'm going to get rejected right away. But in such a simple band structure, we can do it. So we can look at the energy distribution curve. First at the Fermi momentum as a function of temperature. And we see clearly that at the bulk TC, there is a finite energy gap. The horizontal axis is energy. And this gap only closes at some temperatures substantially above TC. We can double check by shifting away from the Fermi momentum by looking at the energy momentum dispersion at the pi0 point proper, like the exact pi0 point. And we see that now even though the band did not directly cross EF, but because it's so shallow that the opening of a superconducting gap actually serves to push the pi0 spectral weight down to higher binding energy in a very appreciable way, going from high temperature into the superconducting state. And again, we see that this downshift of the pi0 spectra started at about 20 Kelvin above TC already. So with all that being said, we think there's a clear photoemission single particle spectral signature showing superconducting gap already opening at almost 30% above TC in such a metallic system.
But how can I mean, how do I know for sure it's not simply due to your oxygen is inhomogeneous?
Yes, we expected that question. So one thing is, we do have a well-defined singularity in the thermodynamic signatures.
No, but this means the most sample is in that TC, right? You have a slight distribution of TC.
Yeah, so that's why we also have the diamagnetic signal. So, yes. So if we were to have any real bulk superconductivity at such high temperature range above TC, we should see a comparable portion of diamagnetic signal in the Meissner effect. However,
how much percentage you'd expect?
So if we look at the spectral wave from ARPAS, it's going to be at least in the 10s to 20% of the spectral wave depletion above TC. But here we see less than 1,000th of diamagnetic signal comparing to when the full superconductivity is reached. So that's one thing that we think it's really important to have a multimodal approach when we try to look at these complicated systems. Yeah. So
sorry, I missed something you just said. You said you do not see the diamagnetic features above TC, above 66 Kelvin, or you do?
He does not.
We do not see appreciable diamagnetic signal.
Yeah, he's claiming there's a gap, but no superconductivity.
So, oh, I see. So you're saying it's not fluctuating. It doesn't matter whether it's fluctuating superconductivity or sample inhomogeneity. One should see some degree of diamagnetic signal. Is that? And you don't see that. Is that the argument?
Key is capacity. Yeah, the key is key capacity measurement. But your heat capacity measurement is sort of kind of broad, right?
Yeah, exactly. That's the point. So heat capacity actually supports the presence of fluctuation. Chimiao, to answer your question, so in the presence of fluctuating superconductivity, there will be diamagnetism, but the diamagnetism will not be directly proportional to the gap, but it will be proportional to the superfluid density. Because in order to form the diamagnetism, you have to actually have global phase coherence to some extent to form those diamagnetic currents. That's why above TC, even though there can be prepared Cooper pairs, the diamagnetic response is disproportionately weaker than what you would get in the bulk superconducting state.
And this, for you, this is an argument that it's more in line with a very clean homogeneous system showing fluctuating superconductivity than showing some sample inhomogeneity. I just want to understand the argument.
That's the first layer of understanding that I intend you to bear
that's fair
with
enough.
at this moment.
That's fair. That's good. Thank you. Yeah.
Okay, sure. Okay, so we can be a little bit more quantitative and fit the spectral peak, position, line width, and the intensity, just pro forma. So what is shown here is a fitted peak position, which should be a measure of the gap at two different momentum. There can also be the peak intensity, and there is also the peak width. So what's really interesting is, even though the gap already opened at a temperature above TC, the peak intensity really and the peak width really only start to evolve once the bulk superconductivity sets in at a lower temperature. So this is the first time we actually have seen two separate signatures on the same set of single particle spectra of both the pairing and the formation of quote unquote superconducting phase coherence. So there's another signature. So we can look at the single particle spectral intensity at zero energy. You can view it as some kind of local density of state just around the antinode, which are plotted as the yellow and the blue dots. And you see that these intensity initially increases as we lower temperature, just like in a metal, as Fermi surface sharpens, but then it starts to plummet at a temperature that's much higher than TC. And to make sure that we're measuring something bulk instead of representative of the bulk property instead of just surface, we also measured NMR in these samples, which can be taken as an overall momentum average of these zero energy density of state. And you see that there is a consistent behavior where the density of state initially increases as we lower temperature, as you expect in a metallic system, and then start to plummet at a temperature much higher than TC. So that is to say, there is a pairing temperature scale much higher than TC, but there is also a bulk TC that is signified by the sudden formation of the quasi-particle coherence in the single particle spectrum. So last but not least, if we were to use the gap opening temperature as the temperature we plug into the delta over kBTC, then we can actually finally bring down the gap to TC ratio to what you would expect in a weakly coupled BCS superconductor. So I think a quick summary of this part is with the new coordinated measurement, both thermodynamic, NMR, and photoemission, we see that the previous understanding of the phase diagram might need to have some major reconstruction in the overdoped side, where it's still the phase coherence that limits the superconductivity. And the mean field pairing strength, while it drops, but it's not really the limiting factor for the pairing, for the superconducting pairing. I think in the interest of time, I'm going to skip some of these parts, and I'm just going to go to the conclusion. We gathered those experimental observations in the heavily overdoped Abyssco. There's a metallic normal state. There's very nice D-wave gap form. BCS gap to TC ratio, if we were to replace TC by T gap, it also falls back onto weak coupling D-wave limit. We show in a separate work that bosonic mode coupling also becomes really, really weak. So we see that BCS predictions almost work, except for this band structure nuance where we have a flat and shallow electronic structure near the zone boundary. And there is subsequently a substantial superconducting fluctuation there. We have more microscopic models with quantum Monte Carlo calculations to justify how a flat electronic structure can enhance such fluctuations beyond the simple mean field. But we'll not have time for it today. So to the very end, I want to say that go back to these two questions we want to ask today. First is, how conventional is overdoped to cuprates after all? I think what we can say is it's almost conventional, except for the band structure peculiarity and the substantial fluctuating superconductivity. And if we can say anything about high TC mechanism, we know that it really looks like a weakly coupled superconductor emerging from a metallic normal state with very well-defined quasi-particles. And the only peculiarity is that phase coherence is still the limiting factor for superconductivity to an extent that the entire superconducting dome that we have investigated so far. I'm going to go to the outlook and to stimulate some thoughts. First, we intend to promote the overdoped visco as a platform to finally search for the pairing mechanism, now that the normal state property and superconducting state property start to behave very well. But there's a plot twist that we both looked into the electron-phonon coupling strength, which plummets in the overdoped range, and also measured with Bob Virginal group in Berkeley, the magnetic excitation strength in visco. And in the overdoped side, magnetic excitation is also extremely weak, more than an order of magnitude weaker than optimal doping. So it really calls into question whether the concept of a pairing glue, a low energy pairing boson, whether that's existent at all. And if it's not there, then we really need to come up with new theoretical frameworks to explain what can still substantiate this 66 Kelvin high TC superconductor coming out of metallic normal state. And I can't emphasize more that enough that targeted material engineering effort is really important. If we can do, say, targeted engineering of interstitial layers or spacer layers, or to targetedly enhance phase coherence between layers, we may actually gain some grounds in our effort to increase DC. All right, that'll be all for today. Thank you so much for bearing with me so far.
That was really a fantastic talk. Questions?
Could I ask a question?
Sure.
It's about your interpretation, and I guess what you just said in the very end was the outlook. So correct me if I'm wrong. Would I be correct in saying that one way to understand the observations is that you definitely have some fluctuating superconductivity that seems to be limited by phase coherence, and that happens in overdoped region, and yet you see some semblance of opening up a gap, up to about what you call T gap, which is about 30% above TC, correct?
Yeah.
Now, would that be inconsistent to say, okay, well, you may have some preformed pairs, however, they're not coherent, and that coherence eventually onsets below TC. That's where you start seeing Meissner effect, whereas above they're just preformed pairs. And none of that would contradict the idea that you still need a pairing glue. So why is it that in your last slide you say, well, maybe pairing glue is out of the question? So what exactly did you mean by that remark?
Yeah, so let me first apologize for this last minute interjection. This questioning of the presence of or existence of pairing glue doesn't have immediate relation to the fluctuating superconductivity that I just introduced. It was more, when I initially structured the talk, it was more as a next step. The reason was because we checked the most prominent electron-phonon coupling type in this overdoped region, and it's almost non-existent at 22% doping. And then we also measured the magnetic excitation in those systems, and it's more than an order of magnitude weaker than what you would have in a near optimally doped sample. So the two leading candidates of low energy pairing boson are seemingly out of the picture. But nonetheless, it's contrasted with the observation that the system seemed to still follow what a weak coupling theory would predict it to behave. A 2 delta over kBTC ratio being normal state being metallic. Then these two observations seem to contradict each other. Not to say that pairing glue is not there, it's just we're struggling to find that mysterious boson if it were to be in place.
I see. And if I may just very quick follow-up. So the nature of the fluctuation superconductivity you've explained very nicely and showed proof from different experiments. How am I to tie this up with the ARPA signature of that nearly flat band that you see near M point? That, I guess, the part that I missed. So where
yeah,
is
that's the part I skipped.
but just to give you an idea, I mean, for instance, there are materials like iron selenide, which you believe to be even closer to BEC limit, where EF is tiny. So for all purposes, you could say, you know, my gap, my EF is like less than 10 milli-electron volt. That's how tiny that is. And yet the fact that you have very small EF doesn't mean that superconductivity have to be strongly fluctuating. So where is the connection?
Right. So what we found really interesting, I'm glad you brought up the iron selenide, iron tellurium selenium example. So for those who are not as familiar of this system in the audience, this is a system where you have a very, very shallow gamma hole pocket in the electronic structure, where the hole pocket Fermi energy is comparable or even smaller than the superconducting gap size. And those are the systems where people suggested there can be a solid state BEC limit. But what we found peculiar in Cuprate is that even though we have a very shallow flat Van Hove point, the overall Fermi energy is still much, much larger than the superconducting pairing energy. So we are thus motivated to ask a question, in the case where we only have part of the momentum space being deformed to be very flat and shallow close to EF, can that actually give us enhanced pairing fluctuation? You know, in the spirit of BCS BEC crossover, even though we clearly know it's not a BEC regime, it's a BCS regime. So with that in mind, we did, first off, we can already have a physical intuition by looking at the Fermi velocity. So in those partially flat shallow band, the Fermi velocity is really, really low. So even if we were to just come from textbook BCS, that will give us a really, really short correlation length. And a shorter correlation length gives us a much smaller correlation volume, and thus give us a very few number of Cooper pairs if overlapping at all within that correlation volume. Therefore, there is an innate tendency to have stronger fluctuation, even just from arguing from BCS picture. But of course, we know it's not self-consistent arguing that way because BCS theory has to assume a mean field. So we want to check with a numerically exact model. So we plug in this toy model where superconductivity is generated by a plain B1G type of electron-phonon coupling. And there's no correlation. So it's just an anisotropic superconducting model. And we plug in this model two different band structures. Both two have the same carrier concentration or Fermi surface volume. One with a highly dispersive band, the other with a band that very much mimics the experimental observation. And we can see that because it's a sign problem free quantum Monte Carlo, we can calculate to very low temperatures. And what we can see is that if we were to look at the spectrum just at the antinode for the steep band situation, we see the superconducting pairing temperature is about 1/24 T. T is a hopping. But for the system where there's a partially flat band near the antinode, the pairing temperature or fluctuation temperature is enhanced by almost 30%, 30 to 40%. So there's indeed a merit to our earlier physical intuition argument that a partially flat band in momentum space can nonetheless still enhance pairing fluctuation, especially in this case in cuprate. The pairing action predominantly happens between the antinodes. That's where the band is flat and shallow. So that's sort of our physical understanding that I skipped.
Great, thanks.
Sure.
I have a quick question. So this overdoped regime in Bisco 2212, how much can you get to larger, but just from a materials perspective, can you get larger doping even?
This is a part I should feel ashamed. So far, with 400 bar oxygen high pressure annealing, that's 400 times atmospheric pressure of oxygen, we can press up to 24% Hove into the system. To put it to scale, superconductivity disappears at this nominal doping of 27%. On the other hand, when we do photoemission, we can do ozone surface treatment. So in this case, it's no longer a bulk doping, but we can selectively just heavily oxidize the surface. Some of these preliminary data shown by the Brookhaven group that they can reach to, I think, 29 or 30% doping, where superconductivity is killed. The problem with those type of surface treatment is that you can't really have intrinsic measurement of TC. So it all comes from a guesstimation of the measured gap and Fermi surface volume.
So for the 24%, how low is the TC?
50 Kelvin.
Oh, okay, still too high.
Too high for what?
Yeah, for like a measuring true normal state, ground state, Fermi surface.
Oh,
I see.
With the field, yeah, okay.
Yeah, so you don't need the quantum oscillations and all these things, right?
I see.
So can I ask you a question?
Yes, please, Puncher.
Yeah, okay, yeah. So in the overdope side, I mean, I thought that many years ago, I mean, there was this story, right? Overdope side is composed of a sort of a sandwich of, not sandwich, I mean, like a Swiss cheese type of model, right? Part of it is non-superconducting, part of it is superconducting. And you mentioned that the magnetism, goes away very small. I mean, could it be that simply because in the overdope side, the sample itself, on a scale of, much smaller than your probe size, that it's actually inhomogeneous? I mean, are there really STM measurements that show that the superconducting volume fraction in this overdope regime, what happens? In local, local measurement, yeah.
Yeah, I'm sorry that I didn't include Ali Yazdani's data in 2010. He actually measured temperature-dependent STS spectrum in this 22% doped Bisco. And what he saw is there are puddles of superconductivity on nanometer scale happening in maybe 5 to 10K above TC. So this is actually, I don't think it's inconsistent. Actually, I think it's in perfect consistency with what we see in photoemission. In this case, the lack of global phase coherence and the presence of nanoscale disorder effect can actually help to suppress the superfluid density or disrupt the phase coherence. But there is one catch to the argument, or to the only argument of disorder. The argument is the following. Experimentally, both from photoemission and from STM, people have seen sharpening quasi-particles or more and more narrowed distribution of superconducting gaps, or narrow and narrow single particle peak width as we go from optimal doping to overdoping. So if this entire effect were just solely coming from increased disorder, then these observations seems to suggest against increasing disorder as we push more oxygen into the system, at least to the extent that a single particle or electron or holes fail.
Right.
So what's really interesting is from the QMC simulation, we found out that the partially flat antinodal region can dramatically enhance the disordered scattering between pi points, between antinodes. And when the very shallow and flat band near endpoint, near pi zero, is combined with the presence of disorder, it can actually serve to additionally suppress both the pairing size and the phase coherence. Simply because pi here is the density of state hotspot and it's sign changing. So it will break pairs in the D-wave superconductor.
Okay, yeah. So it'd be nice to see this on YBCO. I mean, I'd be much more, comfortable. I mean, if you see a YBCO really clean system, then yeah.
Yeah, I agree. It's just that photoemission on YBCO is very difficult because the surface is polar. Yeah.
Okay, very good. Thank you.
Sure.
Any other questions?
Oh, there's something in chat.
Oh, Doug had to go.
Doug has to go. Yeah, okay.
Yeah. Okay. You didn't have any questions? I guess not. If not, thank you very much for this very, very, very
interesting.